All right, everybody. Obviously, I'm not here at school, but we still have to take notes. So I have recorded this video for you to hopefully keep us on track. So today we are going to take 3-3 notes over linear functions. So you'll need your spiral notebook. So go ahead and get that out. And then you're going to flip to your Unit 3 Table of Contents page. Like I said, it's going to be section 3.3 or notes 3.3. And today we are finally going to take a look at linear functions. So linear functions, and we're going to tape this down onto page 21. So again, that's section 3.3. Title is linear functions, and we're going to tape it down on page 21. So everybody should be writing that down. This is the set of notes. The sub will get it passed out. You're gonna tape this, fold it in half first, of course. Fold it in half and then tape it down onto page 21. So I'm gonna let the sub pause this video and give you guys enough time to get that done. Okay? Okay, so by now we should have this taped down onto page 21. Again, if it's not taped down onto page 21, you will need to get that done before we start taking the notes. All right, so now that everybody's caught up, we are gonna finally talk about linear functions. This is what you guys spent a majority of your 8th grade year talking about. And so we've got to get the definition of a linear function, some important to know information, and then we can start looking at some practice problems. So to start up here, it says a linear function in two variables, x and y, is an equation that can be written in the form y equals mx plus b, where m and b are constants. Now, normally when kids come out of middle school, this is like the only formula they can remember is y equals mx plus b. This is what linear functions look like when they're written in equations. So this is a really important form for us to know for equations. All right, so now let's talk about the 4 things that I need you to know about linear functions before we ever look at any kind of practice problem. So the first one is a linear equation can always be written in y equals mx plus b. This particular equation is called slope-intercept form. So slope-intercept form. So if you guys ever hear me say slope-intercept form, this is what I'm talking about, y equals mx plus b. I never really say y equals mx plus b. I'll always call it slope-intercept form instead, so make sure you know that. The second thing, the graph of a linear equation is a straight line. Is a straight line. You won't see any curves in a linear function. One thing that I've had some kids tell me in the past is when you look at the word linear, it has line in it, so they equate that to a straight line in their head, and that's how they remember that a linear function is a straight line. Now, number 3 is a follow-up to number 2. A linear function is a non-vertical line. So it's a straight line, but it cannot be a vertical line, and I'm going to explain that, so finish writing non-vertical. Now, what we're saying is a linear function can be any straight line as long as it's not a vertical line. So here's our coordinate plane. Here it is. If you have a vertical line right here and you do that function test, the vertical line test, it does not pass, which means it is not a function. That's why it cannot be a vertical line. Okay? So it can be a straight line, literally any other straight line but the straight vertical one, because it doesn't pass that function test. All right, and the last one, that final one, it says a linear function has a constant rate of change. Rate of change. A linear function has a constant rate of change. This is also called slope. And a lot of middle school teachers have this lovely little bulletin board where they have rate of change and slope on that board talking about the m. That's going to be the m variable that you've got in your slope-intercept form. All right, now that we've got that important information down, we are going to practice simply identifying if a function is linear or not. So there's some different scenarios that you might be given. I've got two very simple ones. I've got a graph, or if you're given an XY table. This is where you have the ordered pairs. So up here at the top, it says identify linear functions using graphs, and then the question says, does the graph represent a linear or nonlinear function? So this is what we're answering, linear or nonlinear. You just look to see if it's a straight line. If it is a straight line, it's linear. If it's not a straight line, it's nonlinear. So when you look at this one's a U shape, not a straight line. So this one's gonna be nonlinear. And then number 2 over here, this one is a straight line. It's slanted upward. It's like it's going up a hill. So this one is linear because it is a straight line. Next up is identifying linear functions using a table. So again, the question says, does the table represent a linear or nonlinear function? So the thing that you've got to remember for linear functions is that they increase or decrease by a constant rate of change. So that means, those are some fancy words. I always look for the pattern that's happening within these numbers. So we're gonna practice this. We're gonna find the pattern of these x values and the pattern of these y values. If they are constant, which means they are the same over and over and over, it'll be a linear function. And if it's not, it's nonlinear. So let's try it. Let's practice. First thing we need to do is get the pattern that's happening with these x values right here. So that's what do you have to add or subtract or multiply by to make this jump. I do want you to focus on add and subtract because that is linear. And so to make the jump from 3 to 6, that's plus 3. The jump from 6 to 9 is plus 3 again. And then from 9 to 12 is plus 3 again. So this is the same number over and over on the top, which is good. So far it's set up to be linear, but we also have to check this part. This part also has to be constant. So now we're making the jump from 36 to 30. That one's going down, so it's going to be subtract 6. Making the jump from 30 to 24, again, that's going to be minus 6. And then 24 to 18, minus 6. Now, sometimes you're going to have numbers that aren't as nice as those. Just type it in your calculator, and it just needs to be the same thing over and over and over. So because these are the same, we have the same pattern happening in the x and the same pattern happening over and over in the y. That means that we have a constant rate of change. And I'm going to abbreviate rate of change as ROC, which means this is linear. So again, if you've got a constant rate of change, it's going to be linear. If it's not constant, nonlinear. So now let's try this one. Again, I'm going to start with the x just because that's the one that's on top. So we have 1 to 3.5. So if I can't figure this out, I would type in my calculator 3.5 minus 1 to figure out that it is being added by 2.5. And then on to the next one. And so then in my calculator, I would type in 3.5 plus 2.5 to see if it gave me 6. And it would. So 2.5. And then again over here on this side, plus 2.5. So we have the same number across our x variable. Again, I've got to check the y variable to make sure that it is the same number across all of them. And so when I do this, 2 to 9, that's going to be plus 7. 9 to 20 is plus 11, and then 20 to 35 is plus 15. Now, hopefully you're seeing that these are not the same numbers, which means this is nonlinear. This does not have a constant rate of change. So again, to make sure that everybody is clear on this one, constant rate of change means that the values, your x variables, increase or decrease by the same number over and over. Y variables increase or decrease by the same number over and over and over. And then nonlinear, it's going to look like this, where you just have like different numbers and it's not the same every time. Now I need you to flip to the inside of that foldable. The last little section that I've got for us to practice identifying linear functions is from equations. Now, the main thing that you have to remember about linear functions and their equations, they are always going to look like this. Remember, this is slope-intercept form. This is what we're after, y equals mx plus b. So I've got 5 equations here. We're just going to simply look to see if this equation matches slope-intercept form. If it does, it's linear. So it just says which of the following equations represent linear functions. So we're just going to circle them, maybe put a check mark by them, whatever you want to do. So this first one, it looks like y equals mx plus b, so this one's good. The second one is not, so that one's going to be a no. The third one, also a no, because it just simply doesn't look like y equals mx plus b, that slope-intercept form that we're after. Now this fourth one here, a lot of kids jump to conclusions sometimes and tell me no because it doesn't like immediately look like this. But in math, you know that we deal with parentheses by distributing. So I'm going to distribute here and then see what happens after that. So when I distribute, because you don't want parentheses, so we need to clear those out. 6 times x, 6x, and then 6 times negative 1 is minus 6. And so now if you compare the simplified version of that back to slope-intercept form, they do match. So this is, in fact, a linear function. It just didn't present itself in slope-intercept form to begin with. And then that last one is definitely not in slope-intercept form, and it's not going to be a linear function. All right, and the final thing that I've got in our notes for today is the discrete versus continuous conversation. So in linear functions, a lot of times you can have discrete graphs, and then a lot of times you can have continuous graphs. So we have to make sure that we know the difference between the two, so that way we can spot them on a test or a quiz or anything like that. So remember the key idea box, these are definitions, and then this is what they actually look like on a number line, and then we can carry that over to the coordinate plane. So it says up there at the top, a discrete domain is a set of input values that consists of only certain numbers in an interval. And I want you to underline certain. Only certain numbers are going to work in that interval. And so here's what I've got for you. So here's my example. It said integers from 1 to 5. The integers are whole numbers, only whole numbers from 1 to 5. So on a number line, I've got dots at 1, 2, 3, 4, and 5. So you only see dots. The decimals are not allowed to be included in there. And so we're not going to have that shading in between. So that's what discrete looks like. It looks like dots on the number line or on a graph. Now, the flip side of that is a continuous domain. Is a set of all input values that consist of all numbers. And I want you to underline all numbers in that interval. And so here was the example that I came up with. It says all numbers from 1 to 5. So when it says all numbers like that, that means we can also include the decimals that fall in between the whole numbers. And so when you look on the number line, I've got it from 0 to 5, and it's shaded in between there this time. If your shading isn't very visible, then go ahead and make it a little bit better for you to see, because mine wasn't all that visible. Now it is. So it has to be shaded because we need all of the numbers that fall between 1 and 5. That includes all of the decimals. So again, discrete is a graph made up of dots. A continuous graph is a line. And so here's how I think about it. And this is, I'm not even sure what middle school teacher told me this way back then, but when I was in middle school, they told me if you have a graph full of dots, it's discrete. And if you have a graph that you can draw the entire thing without lifting your pencil, then it's continuous. So again, discrete is the dots, continuous is going to be the line that you can actually draw without lifting up your pencil. So now let's take a look at these two example problems. These are the two I'm going to work with you through before I let you try the ones on the right on your own. So it says, find the domain of the function represented by the graph and determine whether the domain is discrete or continuous. Oops, I kind of already done that for you, but we'll write it down at the end. So, problem number 1, it says buying tickets to a museum, a max number of tickets is 4. So, this one's going to be dots because, and here's what it looks like. This is the number of tickets that you buy versus the cost that it cost you. So we have $0, 0 tickets. This one, it was 1 ticket for $15.95. Then we had 2 tickets for $31.90, 3 tickets for $47.85, and then 4 tickets for $63.80. And then it said up there that we had a max of 4 tickets, so you cannot go past 4. Now, the reason, so we had talked about this one was a discrete graph because it has dots. You can't have the middle because this is what something costs. It's just, it is what it is. It's going to cost this much. So we have to figure out what the domain is. So let's go ahead and write discrete because I accidentally told us what that was earlier. So it is a discrete graph because of the dots. And now the domain, and we just, math people, we use a capital D to represent domain. Now, you need to remember that your domain values are the x values of the situation. And so when you look at these ordered pairs that are on this graph, the x values are 0, 1, 2, 3, and 4 because our x represents the number of tickets that we can buy. And so we can buy 0 tickets, 1, 2, 3, or 4. And I did use set notation brackets, those little squiggly brackets. You need to write your domain like this if you have a graph of dots like this. If it's not dots, then you won't use those set notation brackets. You'll use the inequalities instead. All right, so now let's try a different one. So this was our discrete graph because it was made of dots. This one is going to be continuous, so we'll go ahead and write this down. And again, the reason this one is continuous is because I can draw that entire graph without lifting my pencil. It includes all of the decimals in between the whole numbers, and so it's going to be continuous. Now here's the situation, because I didn't even read that part. An anteater consumes about 35,000 insects each day. And so we have the number of days versus the number of insects that they eat. So at day 1, it's roughly about 35,000. Day 2, just under 75,000. Day 3, a little over 100,000. And so this is going to keep track right here. Now, we need to chat about this arrow right here. Every time I ask you guys what that arrow means, you proudly say it goes on forever, which is great. In this particular situation, this arrow represents the number of days continue to pass. This little anteater's still eating on some insects. And so there, it's going to continue on until that anteater dies, and then obviously it'll stop. Now, for the domain, we have to figure out where does the x value start, aka the number of days, and then where does it end, that kind of situation. So again, capital D for the domain. We have x, because we're talking about our x values here. And I'm going to highlight something right here. This starts at 0 days. That's when they started keeping track of how much this anteater was actually eating. Now, this has an arrow on the end because it does go on forever or until the anteater dies, but we don't know what day that is yet, and so we can't assume. And so how we write it is x is going to be greater than or equal to 0. This means that we're going to start keeping track on day 0 and every day after that, which is greater than 0. Now, the main part of this little section right here was, can you identify discrete versus continuous, and then can you start thinking about domain in context of whatever scenario that you might be given. So here's what I'd like you to do now. At your desk by yourself, don't move around. This is an individual little time frame. I need you to try problems 1 through 8 on your own. all you are doing, it says determine whether the following represents a linear or nonlinear function. So you've got 8 different representations. You're trying to determine if it's linear or nonlinear. So you do that. Look back at the front of your notes if you have to. I'm going to have the sub pause this video and give you guys, we'll say 6 minutes. 6 minutes to complete these problems, and then we'll push play again after 6 minutes and do that final one. All right, y'all go ahead and start. Your 6 minutes should be up now, so I'm going to show you what the correct answers are to make sure that you have the correct answers in your notes. There's only one that I'd really like to talk about, so rapid fire. Number 1, nonlinear. 2, linear. 3, nonlinear. 4, linear. 5, nonlinear. 6, nonlinear. 7, linear, and 8 linear. I only want to talk about number 7. A lot of kids last year wrote that this one was nonlinear because it wasn't in the correct form. It actually is. You just have to swap these two and put it back into that slope-intercept form and make it look like y equals mx plus b. So double check before you claim nonlinear or linear and make sure that the form is in standard form. So variables should always be listed first. And then last year I had a couple kids get confused because they weren't quite sure that there could be fractions. There can be. They're still numbers. And so this one's also going to be linear. Now let's take a look at that final problem that we've got down there. This is our real life problem. So here's what it says. The amount of air in a scuba diving tank with a capacity of 2,400 liters is decreasing at a rate of 48 liters per minute. So I'm going to write decreasing. That's going to show me that my line is going down because we're running out of air in that scuba tank. And so here's part A. It says, is the amount of air in the tank a function of the number of minutes? So before we can answer this question, we have to be able to write an equation for this given scenario. So I'm going to think about slope-intercept form. So y equals mx plus b. So right here, I'm going to have y equals, we started with 2,400 liters, okay? I'm going to put that at the back because that's my initial value. That's where it starts, okay? So 2,400 liters. And it is decreasing, so that means I'm going to have a negative slope by 48 liters per minute. And so here's the equation. And we're going to practice writing linear equations a little bit later. But it's y equals negative 48x. This represents losing 48 liters per minute out of the 2,400 that we originally had. So since I was able to write this as an equation in slope-intercept form, that means it is a function. So the answer to part A is yes. Now, part B says sketch the graph of the function. And so we're going to, sketch means just about, it doesn't have to be 100% accurate. So here's what we're going to do. 2,400, we're just going to plot that point right there. Because at 0 minutes, we still have 2,400 liters in our little scuba tank. Now, I'm going to use a calculator because I made sure that I had a calculator before I did this. I'm going to plug in 20 minutes to see how much is left, and so we can plot that dot. So negative 48 times 20 minutes. We got about 1,440, so 1,440 at that 20-minute mark. So that's, again, almost kind of halfway in between 1,000 and 2,000 at 20 minutes. Now I'm going to check at 40. So same thing, I'm just plugging in my 40 minutes because I'm trying to sketch out this graph. So at 40 minutes, we only have 480 liters left, which is a little bit less than half. So about right there. Now, I think that it's going to run out of air before we get to 60, so I'm going to try this middle mark right here. So negative 48, that's 50 minutes, by the way. Ooh, and that is when it runs out. So at 50 minutes, we hit 0. Now that we've got our dots, we need to draw a line that represents this scuba tank losing the air. We do have to include the lines in between the dots because this is time and we're losing air. So it's not like it goes for a minute and stops. It loses at a constant rate. So part B is done. It says sketch the graph. Got it. Part C, find the domain of the function. Is the domain discrete or continuous? So hopefully by now, since we did that work over there, you know that this graph right here is continuous because you can draw the entire thing without picking your pen up or your pencil up, and it's not made of dots. So we're going to write continuous. Continuous. Now we're going to talk about the domain. The domain, remember, is the x value, okay? So we're talking about time, and so if I'm going to do my little trick where I highlight the beginning and the end, it starts here at 0, so it's 0 minutes, and it runs out right here at 50 minutes. That means the time frame that I've got to use this scuba tank is anywhere between 0 and 50 minutes. I better be above water and breathing oxygen at that 50-minute mark. So how we write this mathematically is we have 0 is less than or equal to x, which is less than or equal to 50. Writing it this way is going to show you the time frame, because remember x is your time frame. The time frame that you're allowed to use that scuba tank before it runs out of oxygen completely is anywhere between 0 and 50 minutes. All right, very good. I am happy that we finally got to talk about linear functions. Make sure that this is taped into your notebook. Good job.